Welcome everyone. Let's work on a planar truss in Femap. This is the planar setup that we are interested in recreating. We see three bars. We have a roller here, a pin, and here we have a force that is acting on a 45-degree angle. Alright, we're gonna try to recreate this in Femap, make our nodes, elements, and so on. Alright, let's get started. First, I'm gonna turn on my work plane so I can have a better visualization where I'm working. So I'm gonna add some dots, uniform grid, 0.5, the spacing between the grid lines. We're gonna leave this as is. We're gonna do snap to grid, and I'm gonna put lines. Go ahead. And there you go. There you have it. Okay, to get started with our geometry, which will be these three lines, I'm gonna go to geometry and use a curve line and go down to continuous. My first point is gonna be at the origin, so right here, 0, 0, click OK. I'm gonna make it be 2 meters long in the X direction, so let's put a 2 there. Okay, and the other one up top for the triangle, that's gonna be 0 and 2 in the Y. There you go, there you go. And I don't really need to come back from the top back to 0 because it was a polyline. So if I click cancel, it will ask me, do I want to close the starting and ending point? I can say yes, and there you go, it closed it for me. So our triangle is nicely done. Very good. Let's click on visualization, turn all the stuff out that we don't want, and I'm just going to turn on the curve identities and the point identities. Alright, done. Very good. Maybe I'll turn my work plane off because now it is just getting in the way. Okay, very good. There you go. Geometry complete. Alright, so the reason why I turned the identities on for the curves and the nodes, because it is very good to see what's going on. If we have everything off, it looks good, but if we have, for example, these two on, we have a little more insight into what is happening, and we can tell something that will give us a headache further down the road. So we can see we have one curve here, another one here, and another one here. Now what do we see here, here, and here? We have 3 points, right? But if we look good, can you read the numbers? No, you can't, because there's 2 numbers on top of each other. And that is because it is taking this line with 2 points. Then it added another line with 2 other points. So the line, this line point here and this line's point here are 2 different points, and the same thing here. So we don't have 3 points, we have 6. Okay, and this will cause a lot of headaches and errors. You won't be able to run your simulation. So in order to go around that, we can go file, not file, tools, and go down to the bottom with check and coincident points. Okay, click on coincident points. I want to check. If you would have only a problem somewhere, then you could select only those and run it. I'm gonna select all of them. Make sure you check all of them. Click OK, and this is a tolerance, like some small number. If the two points are closer to each other than this, then it will merge them. Okay, and leave everything as is and click OK. And now what we see? We see 3 beautiful numbers that are actually legible. So that means that we don't have 6 points anymore, we have 3. Okay, next up, let's work on adding material type that we are working with. Let's call it my material. There you go. We're gonna leave this one as is, isotropic. Okay, I'm gonna add, let's 70 E9 for the Young's modulus, and for the Poisson's ratio 0.33. You can add whatever material you want to work with. This is fine for me over here. I'm just using just one material, but if for example you had 3 different materials for each of these, then you could add all 3 and go with that. Okay, next up, let's add properties. I'm gonna use 2 different size rods, so I'm gonna call rod 1. Material is gonna be the one that we defined. Element element property type, it's gonna be rod. Okay, and here I'm gonna use for the first one 0.1 for the area. Okay, and let's enter the second one, rod 2. Same material, same element type, but the area is gonna be, let's say, bigger. Okay, and that's it. I don't need a third one. Very good. Now we are ready to take care of our meshing. First we're gonna seed it, and then we're gonna do the actual meshing. So go to mesh, mesh control, size along the curve. I'm gonna select all my curves. Here's the highlight so you can tell. Okay, now we have 2 options. Number of elements, we can discretize it by 1, 2, 3, whatever we want, right? Or down here we can discretize it by the size of the element. We can add 0.001 for the size, and then it'll fit as many it can with this size that we defined. For me, since this is a planar truss, I need only 1 element per each curve. Okay, there you go. Click cancel. Now we have successfully seeded our mesh. Now we need to do the actual meshing. So geometry, go back to mesh, geometry, curve, and if I would be using the same rod for all 3, I could click select all, but I have defined 2 different rods, right? Let's say I'm going to use rod 1 for this, and this one, number 2, I'm going to use rod number 2. Okay, so this clear selections right here. So let's do the rod number 1 first. I'm going to pick this one and this one. Okay, now I'm gonna pick the property that I defined. See, rod 1, rod 2. For this one we pick rod 1, click OK. Now we go back, mesh, geometry, curve, and now I pick this guy, and there you go, highlighted it. Okay, now for this one I'm gonna pick rod 2. Okay, there you go. Now we have meshed our geometry. So just to double check, bring up visibility. So when we are looking at the cyan color, that is our geometry. We can see our points, see, and we can see our curves. Now if we come up here, we can turn the geometry off, and the white lines, those are our meshes. With this button right here, we can turn that one off too, but then we don't see anything. So let's just leave this one on for now. So let's take a look at the mesh. Bring back up the visibility. Visibility you can access by Control Q or in the view option. So see, points and curves do not appear on the mesh. Points and curves belong to geometry. In the mesh we have elements and nodes. Okay, make sure you remember that. So we have 1, 2, 3, those are the nodes of the mesh, and 1, 2, and 3, those are our elements. We have 3 elements. Okay, and we can click OK. I'll put my geometry back on, and we are ready to apply our boundary conditions. Now when we go to model, and let's see the constraints. Now we have 2 options. when we want to apply a constraint, let's say work on point 1 right here, right? I want to apply my constraint. I have two options: either do a nodal constraint or a point constraint. So what does that mean? Here we need a pin, right? We're gonna need a pin. So in order to put a pin here, we're gonna have to apply this constraint on a node or on a point. What is the difference between the two? Points belong to the geometry. So when we would apply on a point, on a cyan blue geometry, the material that we're working with, right? That's where it would be applied. If I add a constraint on the node, then it would be applied on the white, on the mesh only. Now, what's the difference between these two? If something goes wrong with your simulation further down the road, let's say you're working on some big project, not on just 3 lines, right? You're working on some pressure vessel, on a truck or a plane or something, and the mesh goes to crap, some error happens, something gets corrupted, you need to delete it, you need to go back to the geometry. Then every single thing, that constraint, load, or anything that you added to the mesh, it will be gone, because you're deleting the mesh. You will delete all its children as well. So therefore, applying constraints and loads to the body, to the actual geometry, is more robust, because you can delete the mesh and redo it and change and do all kinds of things without having to redo all your constraints, loads, and such. All right, so keep that in mind. So for us, we're gonna go ahead and apply our constraints on point. So title, boundary conditions, BC. Okay, I'm gonna pick the point that I'm gonna apply to right here, point 1. Okay, let's see, what is this? Bottom left, bottom left, and we said this is a pin, right? There you go, we select pin. Okay, now what else we have? Let's see our diagram. Oh, this is a roller. That means we have we will allow it to move in this direction, but not in and out of the screen, or in this direction, horizontal. Let's add that onto up here, number 3. Okay, let's see, that's the top one, and this one is arbitrary, and we need to, let's see, we need to allow y to keep moving, but z and x need to be zeroed out. So z and x need to be zeroed out, but the translation in the y is allowed. Okay, and we have our last point right here. Let's see, do we need anything on it? No, we don't need any constraints on it. Oh, we have, no, we don't. There's no constraint. Very good. Okay, we can cancel that out, so we can go ahead and add our loads. Or if you first, before that, let's go back to visualization with Control Q, and what did we do? We did added constraints right here. If you turn these on, the numbers for them will appear. I'm going to turn the nodes and elements on, so only constraints are turned on right now, so we can tell T for all translations zeroed out, and here 1 and 2. The 2, 1 and 3. The 2 is missing because that's, we allowed it. 2 represents y. We allowed it to move. Okay. Alright, so let's go ahead and apply this load, and remember, it needs to be at a 45-degree angle. And what is it? 1000 newtons. Okay, let's apply our load. Again, we're gonna go to model, load, and instead of the node, it's more robust to apply it to the point, right? We're gonna apply it, let's say that's external forces. Okay, we're gonna pick our point. Okay, and it's gonna bring up this window. And one other note is that applying it to the node or the point, it has absolutely no difference when it comes to calculations, because it will join them in calculation wise. They become a family, or the same thing, node or mesh. It doesn't matter which one you apply it to. It just robustness, what we discussed a minute ago, that's where the difference comes in. Calculation wise, it will give you exactly the same result. So back to the force. Let's see, we need to apply a 1000. So we can pick the force title, let's see, force, call it a force, and I can define it by a vector. Okay, so we can give it a magnitude. It called for 1000, and if we go here to specify, it brings up this window, and here we can define it based on unit vectors. So since this is on a 45-degree angle, here we can simply define 1 for x, 1 for y, and 0 for the z, and that will give us exactly a 45-degree. This one we already filled out. You can click OK, and there it is. There's our force vector. Now sometimes I like to see the magnitude written here, so bring back the visualization window, Control Q, and we applied loads, right? So there you go, loads. Oh, that's not the one, force bearing. Well, turn on everything. There you go. See, we got it. We'll turn off. Where is body, force, and there you go. Oh, right under it, we just didn't see. And let's turn back all useful stuff, constraints, maybe nodes and elements. That's it. That's good. I like to see those. Very good. I think we have everything done. We're ready to start the analysis. Go up to analysis, model, analysis, new, title 1, stay in analysis type 1, static. Okay, and go ahead and click analyze. We're gonna wait for the solver to finish its calculations, and over here it should tell us that it's complete, or throw an error that we did something wrong. And there you go, complete. Very good. We can be happy. We didn't do nothing wrong, and it completed the calculation without error. Now let's do some post-processing. Now that the analysis is done, we can, this is the original, right? If we come up here, we can click on this one. We can see the deformed shape, how much it moved out of place. Turn off the, maybe the geometry, the cyan. Then now we can look only the mesh. We can come right here, post options, on deformed. Then here you go, we can see both of them at the same time. This is how original the mesh was with the force applied, and after it moved it out of place this much. Now a lot of times when you look at it like, how come it moved out of place so much, remember that automatically Femap always scales the results by 10. Okay, so this is reality times 10. If you want to see it more closer to reality, put a 1, and then you would see, there you go, just a tiny little bit. Or you can make it more visible. Sometimes it's even 10 is not enough, so you can maybe make it 100, you know. So there you go. This is another thing to help us visualize our tools, our results, or what we need to see. Okay, now let's go ahead and visualize some of our results, see what happened. Okay, let's go back to the original on deformed. There you go. So go to view, select or options. These are the two best friends of post-processing. Okay, so hidden line, deform, beam diagram. Down here we're gonna go ahead, and we were working with rod, so rod, axial force, where is it? Rod right here. Oh no, that's stress. Oh, rod axial force. Let's see, let's visualize the internal forces in these diagram beams. Right, there you go. We can see which one is in tension, which one is in compression. Here you can tell your values. You can double check rod axial force, make sure you picked what you needed. We can even visualize the values at these locations. Go to view, options, post-processing, beam diagram, labels at peaks. Click apply, okay, and now we can see some values, the maximums. There you go. Okay, or if this might be maybe confusing for you because they cross on top of each other, you can go back to the options, and instead of having them displayed along the y-axis, we can, let's say, display them along the z-axis. Apply, okay, see, now it's displayed along the z-axis. Maybe you can understand it this way better. Alright, well, that would be it for this video. Make sure you guys like it, subscribe, and tune in for the next one, and have a good day. Alrighty, bye.